Hello, everyone. My name is Suganya Phantu. Today, I will present my research entitled The Performance of Parametric Control Charts of Zero Inflated Process. This study focused on the performance of parametric control chart for monitoring process that contain an excessive number of zero values. The presentation is divided into four main parts. First, I will introduce the background and research problem. Second, I will explain the research methodology, including the zero-inflated model and the control chart used in this study. Third, I will present the numerical result and real data application. Finally, I summarize the conclusion and future works. Control charts are important tools in statistical control process control. They are used to monitoring process quality and detection of chip and in-process behavior. Traditional Schumann charts are effective for large chip, but they are less sensitivity to small and moderate change. Therefore, more advanced charts such as ELMA, ME, MEMR, and ELMA-ME have been developed to improve detection ability. In this study, these charts are applied to zero-inflated binomial and zero-inflated boson, or ZAB and ZAP data. The main problem is that many real processes contain excessive zero observation. This type of data is called zero-inflated data. If conventional control charts are applied directly, they are not detect small and moderate process shift effectively. Therefore, a more sensitive monitoring approach is needed. This study compares several control chart schemes to determine which one can detect process change more quickly and more reliably. The objective of this research are as follows. First, to evaluate the performance of full control charts, ME, ELMA, ME, ELMA, and ELMA, ME. Second, to compare their performance under two zero-inflated distribution, such as zero-inflated binomial and boson. Third, to identify which paths provide the fastest signal when a process shift occurs. Finally, to demonstrate the practical usefulness of this chart using real-world data. This slide shows development of control chart method used in this study. The ELMA chart was introduced in 1959 and is well known for detective small shift. The MA chart used a moving average of recent observation. Later, hybrid charts such as ME-ELMA and ELMA-ME was developed to combine smoothing mechanisms from both approaches. In this research, all four methods are compared under the same monitoring conditions. This study focused on two zero-inflated models. The first is the zero-inflated binomial model, or ZAB. This model is suitable when cloud data have a binomial structure but contain more zero than expected. The second is zero-inflated boson model, or ZAP. This model is used when cloud data follow a boson pattern but also have excessive zero value. Both models include zero-inflated parameter, which represent the probability of extra zero in the process. The first control chart is the ELMA chart, or exponentially weighted moving average chart. The ELMA statistic give more weight to recent observation while still retaining information from previous data. This makes ELMA very useful for detecting small and moderate shifts in the process mean the chart signal and out of control condition when the statistic exceeds the upper and lower control limits. The second chart is the moving average or MA chart. This chart calculates the average of a fixed number of recent observations. By smoothing short-term fluctuation, the MA chart can help identify meaningful process changes. However, its performance depends on the window Y used in the moving average calculation. The third chart is MA-ELMA chart. This is a hybrid chart that first applies the ELMA idea and then use a moving average structure. The purpose of this hybrid method is to improve smoothing and increasing sensitivity to process shift. In this study, the MA-ELMA chart is compared with the signal chart to evaluate whether the hybrid structure improves performance. The fourth chart is the ELMA-MA chart. This chart combines the moving average and ELMA mechanism in a different order. Like the MA-ELMA chart, it is designed to detect change more effectively by using information from both recent and past observation. The comparison between MA-ELMA and ELMA-MA helps show whether the order of smoothing affects chart performance. The performance of control charts is evaluated using three main indicators: ATS, VRL, and MIL. ATS means average time to signal. A lower ATS indicates faster detection of a process shift. VRL represents the variability of the run range. A small VRL means the chart is more stable. MIL is the median run length and provides another measure of detection performance. In this research, the charts are calibrated so that the in-control ATS is approximately 370, allowing a fair comparison. For the simulation study, the parameters are set separate for ZAB and ZAP data. For the ZAP data, sample size is set to 500 and initial non-conforming proportion are 0.01 and 0.05. For the ZAP model, the zero inflation parameter is set to 0.2 and the Poisson mean value are 1 and 5. Different chip size are tested ranging from very small chip to large chip. This allows us to examine how each chart performs under different levels of process change. This slide presents the result of the zero-infested binomial distribution. Overall, the ELMA chart performs very well for small and moderate chips because it can respond quickly to subtle change. For large chips, the MA becomes more competitive and can sometimes provide the lowest ATS. This means that for ZAB process, ELMA is generally suitable when early detection of small change is important, while MA can be effective when the process chip is large. This slide shows the result for zero-infested Poisson distribution. The findings are clearer for ZAB's case. The ELMA chart consistently achieved the lowest ATS across most chip magnitude. This indicates that ELMA is the most effective chart for detecting chip in ZAP processes. The hybrid chart also improves smoothing, but they are not consistently outperform the poor ELMA chart. And this slide is present the real data application for ZAB model. The full chart are applied to the same data so that their monitoring behavior can be compared visually. The results show that the proposed control chart framework can be used in practical situations where the data contain many zero observations. The chart helps identify potential out-of-control signal and support decision-making in quality monitoring. Next, for the ZAP real data application, the same flow chart are also compared. The result confirmed that the chart can be applied to zero-heavy code data. Among the flow methods, ELMA again shows strong performance because it reacts quickly to change while maintaining smooth monitoring behavior. This support the simulation finding and show the practical value of the method. In conclusion, this study evaluated for parametric control chart from zero infected discrete process. The chart will compare under ZAP and ZAP distribution using the same in-control conditional. The simulation results show that ELMA provides the best overall performance, especially for small and moderate chips. For ZAP process, ELMA consistently gives the fastest detection. For ZAP process, ELMA is also effectively why MA can be competitive for large chips. For the future works, the proposed framework can be extended to also zero-infected and over-dispersed distribution. Adaptive smoothing parameter may also be investigated to improve performance under different process conditions. Another possible direction is to study cases where process parameters are unknown or must be estimated from data. Finally, the method can be applied to real-time industrial monitoring system and broader real-world quality control data sets. And this slide is the list reference to control chart related to ELMA, MA, ELMA, and ELMA, MA. That concludes my presentation. Thank you very much. I would also like to acknowledge the Faculty of Science, Energy and Environment, King Mongkut University of Technology, North Bangkok, Rayong campus, Rayong, Thailand, for supporting this research project. Thank you.